Hello, and welcome to this presentation, Understanding Peak Envelope Power. In this presentation, we'll provide a short technical explanation of peak envelope power in radio frequency applications. Since it's very difficult to measure voltage and current at very high frequencies, RF power is usually measured directly, instead of being calculated as the product of measured voltage and measured current. The most accurate way of measuring RF power is RF power sensors. These sensors may either terminate the RF power or may be placed in line so as to make directional power measurements, that is, simultaneous measurements of both forward and reflected power. RF power sensors are often categorized by how they measure power, for example, thermal, average power, diode, etc. And the type of sensor will affect things such as its accuracy, power measurement range, frequency range, measurement speed, etc. Regardless of sensor type, it's relatively easy to measure the average or peak power of a constant amplitude signal, such as an unmodulated or CW signal. And in this case, the average power and the peak power will be the same. However, measuring the amplitude of a signal whose amplitude changes over time can be much more challenging. AM or amplitude modulated signals, including single sideband signals, would fall into this category, but there are other types of signals with time-varying power. For example, those which use modulation schemes such as QAM or APSK, which are a combination of both amplitude and phase modulation. We can quantify time-varying power in four ways: instantaneous power, average power, envelope power, and peak envelope power. In the remainder of this presentation, we'll explain each of these step by step. Instantaneous power is the power at any given instant, or at any given point along the waveform. At RF, this power is changing very rapidly, with frequencies from the mid-kilohertz well into the gigahertz range. An oscilloscope or other digitizer with sufficient bandwidth could acquire and accurately measure this waveform, and then determine the peak instantaneous power. But this is often impractical over longer periods of time. RF power sensors usually cannot measure rapidly enough to accurately measure instantaneous power, but in practice we're usually not interested in individual RF waveform cycles, but rather the average power over a larger number of cycles. A signal's envelope is defined as the average power over one period of the carrier. For example, in the figure on the right, this shaded region is one cycle of the RF carrier. The envelope power would be the average power over this single cycle, which we'll represent by this red dot. If we were to repeat this for each carrier cycle, the result would be a line that looks like this, and this line is the envelope power. In most cases, viewing or measuring the envelope is much easier and much more useful than looking at individual RF carrier cycles. An important thing to note is that a sensor's so-called video bandwidth will affect the shape and magnitude of the envelope. Generally speaking, the video bandwidth must be greater than the frequency of the modulating signal. On some sensors, video bandwidth is user-configurable in defined steps or over a given range. It should also be noted that only some RF sensor types, primarily diode-based sensors, are able to measure envelope power. Peak envelope power, therefore, is simply the highest amplitude of the envelope power. This point will occur at the peak of the modulating waveform. Peak envelope power is often used as a practical way to quantify maximum power, and in common usage, the expression peak power normally refers to peak envelope power and not to peak instantaneous power. Because peak envelope power is a practical measure of maximum power, it's often used by standards bodies like the ITU or regulatory agencies like the United States FCC to define maximum output or transmit power, for example when placing limits on transmitter or broadcaster output power. Peak envelope power is also used as a basis or reference for calculating other power-related quantities, such as crest factor, peak-to-average ratio, and the complementary cumulative distribution function, or CCDF. These are all measures of the burstiness of a signal and are particularly important in modern digital modulation schemes. And finally, many test and measurement instruments use peak envelope power when indicating power levels, for example, the output of a signal generator. Let's end with a brief summary. The power of time-varying RF signals can be quantified in four main ways: the instantaneous power of the carrier, the average power over a defined measurement time, the envelope power, which is the average power for each individual carrier cycle, and the peak envelope power, which is the peak of this envelope. Peak envelope power is commonly used as a measure of the maximum amplitude of a radio frequency signal, and it's also used in the calculation of crest factor and other peak-related quantities. In addition, many standards bodies and regulatory agencies set limits in terms of peak envelope power, and peak envelope power is also commonly used with RF test and measurement instruments. This concludes our presentation, Understanding Peak Envelope Power. If you'd like to learn more about radio frequency power measurements or power sensors from Rohde and Schwarz, please see the links in the video description. Thanks for watching.